we're going to do another Lagrange multiplier problem, finding the point on a sphere that is closest to the origin. So you could do this problem without Lagrange multipliers, but it's going to get messy. You could also do it with Lagrange multipliers, and spoiler alert, it also gets messy. But I think the Lagrange multiplier case is interesting, especially because there's parts of the Lagrange multiplier technique that extend a little bit better than some of the approaches you might use for without Lagrange multipliers. So let's just take a quick note. Without Lagrange multipliers, what I might do is I'd try to minimize x squared plus y squared plus z squared, where z squared, using this equation up here, equals 1 minus x minus 1 squared minus y minus 2 squared. And that's doable. It's especially doable because z squared is by itself. If I didn't have z squared by itself, this would get a lot harder. But with Lagrange, we'll see an approach that kind of generalizes a bit better. So I'm going to think, what's my objective function and what's my constraint equation? Or what is kind of the level set involved in my constraint equation? Well, my objective function is essentially exactly what it would be in the single variable case. I'm trying to minimize distance, and whenever you're trying to minimize distance, it's a little easier to minimize distance squared. So I'm going to minimize x squared plus y squared plus z squared. And I'm going to have a constraint equation given by my level set. My constraint equation, or at least the g, the level set, the function that, I'm using for my level set, is going to be x minus y squared, or x minus 1 squared plus y minus 2 squared, not z, plus z squared. And I would go ahead and now take the gradients of each of these. So the gradient of f is going to be 2x, 2y, 2z. The gradient of g is going to be oddly similar. It's going to be 2x minus 1, 2y minus 2, 2z. And we're going to get a system of equations given by 2x equals lambda times 2x minus 1. I don't think I left myself enough room with this system of equations. We'll have 2y equals lambda times 2y minus 2. Parentheses are in the wrong place for both of those. That's great. Good start. And 2z equals lambda times 2z. And last but not least, we have x minus 1 squared plus y minus 2 squared plus z squared equals 1. So those are my constraints. Now, this system of equations is not terribly easy to solve, but let's go ahead and see what we can do. First, this equation's a little interesting. This equation is interesting because if z doesn't equal 0, then lambda has to equal 1. Because then I could divide both sides by 2z. But if lambda equals 1, then we have 2x from our first equation. 2x equals 2x minus 2, which is clearly not true. So we know right now that therefore z has to equal 0. Okay, so we know one thing right now. Z equals 0. But it also means that this equation doesn't really tell us a whole bunch, unfortunately, other than that z equals 0. So now let's look at the others. If we look at other equations, what I found easiest to do in solving this problem is solving each of these for for x and y, for x, y respectively, in terms of lambda. And some nice stuff happens if you do. That's not always a great approach for these problems, but it's worth doing an example where that is a nice approach. So in our first equation, we're going to have 2x equals 2 lambda x minus 2 lambda. That's going to give me, if I rearrange my terms, that's going to give me 2 lambda equals 2 lambda x minus 2x. My 2's are becoming lambdas, unfortunately. 2 lambda x minus 2x. I can divide each side by 2, essentially, to get lambda equals 2x, or sorry, just x, lambda x minus 1. Or minus x, I should say. We just divide it by 2. And then we factor out an x. We get lambda equals x lambda minus 1. We get x equals lambda over lambda minus 1. We can do the same thing for y. We get 2y equals lambda times 2y minus 2. Let's go ahead and just divide by 2 now. We get y equals lambda y minus 2. Or y equals lambda y minus 2 lambda. We can rearrange to get 2 lambda equals lambda y minus y. Doing the same factoring and stuff that we did earlier, we're going to get that y equals 2 lambda over y, lambda minus 1. Okay. And with that, let's go ahead and look at our constraint equation. We know that z squared equals 0. So let's see what the rest of this stuff is going to be. We'll have x minus 1, but we know that x is lambda over lambda minus 1. So we'll have lambda over lambda minus 1 squared plus 2 lambda over lambda minus 1 minus 2 squared equals 1. And that might look horrible, but if you multiply everything by a lambda minus 1 squared, some nice stuff happens. This is going to become lambda minus 1 squared plus 2 lambda minus 2 lambda minus 1 squared equals lambda minus 1 squared. This here will have lambda minus 1, or lambda minus lambda plus 1. So that's going to be 1 squared plus 2 lambda minus 2 lambda plus 2. That's going to be 2 squared equals lambda minus 1 squared. We'll get plus or minus 5 equals lambda minus square root plus or minus square root of 5 equals lambda minus 1. We'll get lambda equals 1 plus or minus square root of 5. So that tells me lambda. It doesn't tell me what x or y equals, but I can then plug it into my original equations to get, well, let's try 1 plus square root of 5. For x, we're going to get x equals 1 plus square root of 5 over 1 plus square root of 5 minus 1. So that's going to be square root of 5. And y will get 2 plus 2 square root of 5 over square root of 5. If we have 1 minus square root of 5, what we'll get is that x equals 1 minus square root of 5 over square root of 5. Plus, and then y equals 2 minus 2 square root of 5 over, actually, let's be careful because I was not careful. This is over negative square root of 5. Similarly, this is over negative square root of 5, which makes sense because I think we can convince ourselves that this won't have any negative x coordinates. So this is then going to be square root of 5 minus 1 over square root of 5, and then 2 square root of 5 minus 2 over square root of 5. And we need to decide which of these two cases is going to give us our minimum distance. And I think you can also convince yourself this is closer to the origin. To the origin. Because if you, yeah. So, there we go. Now, what you might not have noticed here is a nice sophisticated argument for why this is the minimum, like, mathematically. That said, you can come up with that nice mathematical argument, but that's going to use a very involved version of Hessian criteria, which we'll get to later. But for now, this is kind of sufficient justification, at least for me, to show that the closest point, and we'll write a nice sentence here, the closest point is, my x-coordinate is square root of 5 minus 1 over square root of 5. My y-coordinate is 2 square root of 5 minus 2 over square root of 5. And my z-coordinate is 0. So there we go. We have solved that problem using Lagrange multipliers.